And Riley, of course, is like, yeah, that's great for this problem. It's not the problem I asked about, though. Right? So this will be x. So it's 11 and 12. Which one's negative?
12.
Bigger one, so it comes out to negative 11. So this would be x equals,
Oh, just 11.
no,
Oh, wait, negative 11.
yeah, negative 11
And then positive 12.
and 12. Okay, good, right? So if only that was the problem, it would have not been that bad. But I'm arguing that is basically the problem. So the problem we have is e to the 2x minus e to the x minus 132. Somebody help me out. What is e to the x squared? What do you do when you have a power, something with a power raised to another power? What do you do with the powers? Multiply them. So what is e to the x squared? E to the 2x. I don't know if anybody sees how this relates. Why did I put an x here and an x there? Two reasons. Why did I do it and why does it work? Right? Why did I put an x and an x? What's the most basic reason? Because there were two of them, right? So of course we're going to have one there and one there. But why does it work? Because then the middle term has one x. Do you guys see that? So if that was a 4 and that was a 2, I could still do it. I would have just put x squared. I could still cut it in half. Yes? So how many e to the x's do I have here? 2 of them. So I can put one here and one there. What numbers work? 11 and 12. So either e to the x equals
Negative 11.
negative 11. Can you solve that? You can try. Or e to the x equals 12.
Could you just put like a natural log?
Yeah, beautiful.
in front of
Natural
it?
log, you definitely want to use natural log because it will kill e, right? The e is in my way. Stupid e. He's got the x up there. So if I take natural log of both sides, well, what happens here? Natural log of negative 11. Can't do it. How do you quickly remember that? What's a log look like if I graph it? Can everybody show me? No? You guys know what it looks like? What's a logarithm look like? See a lot of interesting swooshes? That's an exponential. So an exponential looks like this. A logarithm looks like this. Can it handle negative inputs? Does it have any out? No, it can't. It can't handle negative inputs. That gives me no answer. That one, I can do the natural log of 12, right? So this is what we call quadratic in form. It is something in the middle, and then that is squared at the beginning. That is quadratic in form. So when I cut it in half, I get the middle term, so it'll work. That's why this works. That's the exact reason why this works. When I cut that in half, the middle term ends up being the correct number of x's. Maybe. So real quick, just to go on that. I'm pretty sure this is something we looked at before. So real quick, what's x squared plus 4x minus 12? How do you factor that? Six and two. Okay, 6 and 2. Which one's negative? The smaller one. I like it. All right, that's great. That's nice. Jeff, do a lot of those. No, none of those will be on the test because we're not testing about this. What about if it was this? Can somebody tell me if this will work? Is this quadratic in form? How many x's are here? 2. How many x's are here? Is this half of this? Why is that important? Because what's the first thing we do to this when we start to factor? We cut it in half. Do you see how the middle terms will now be x's so they match? Is this half of this? Yes. How do I factor this? Well, what's the first thing I do? I cut this thing in half. Do you see how the middle terms will now be x to the fifths? So it's still the same stupid numbers, right? The same numbers work. So anything where the middle variable expression is half of the first variable expression multiplicatively, it's quadratic in form. I can do the exact, just do the numbers thing. What numbers multiply right, what numbers add right. Okay, maybe. So you see a few of these in the homework, and they all work that way. You can break it up just like you could if it was x squared. Now it's e to the x squared. It works the exact same way. Watch this. How would I do this? Oh, we don't know that yet. Let me put this. What do you got, Jeff? Sure. Is that quadratic in form? Is the middle guy half of the first guy multiplicatively? Yes. Right? It doesn't matter what this is, as long as this is half of this. It'll work, because what's the first thing when I go to start to factor it? What would I put here? There's two of these. So what do I put here and here? Yeah, I put one. So that when I FOIL it, bam, it makes two again. That's why it works. And what's the middle term going to be now? The middle term is going to be sine x. What numbers work? See, the process doesn't give a shit. The process doesn't care. If it was x squared plus 2x minus 48, we would have put x and then done the numbers, right? We would have done that. Because I cut the first dude in half. And why does it work? Because then it will make the correct middle term. If this was 4 and this was 1, no. No, it's not going to work. When I cut that first dude in half, how can it make the middle term? Right? Maybe. So when I cut this guy in half, what would I get? X squared. Can that ever make that middle term? No. So that's why the middle term has got to be half, multiplicatively, the first guy. So what numbers work?
8 and 6.
8 and 6. And the bigger one is positive. Okay. So that's an example of an underlying idea that we can put on top of all these different situations. It's not different things to memorize. It's the same exact idea. Maybe. Okay. All right. I went way off on the team. So today it's wide open. I've got a few things I want to do, but I want to start with any questions you guys have. Let me give out the other quizzes here real quick. All right, so today is the day. Today's the day to just be like, Jeff, can you just freaking try to start over? What the hell sign? Whatever, right? Is there something that hasn't made sense at all yet? Is there something that you just have a little bit of trouble with? Is there something you completely don't understand? Today's the day to get it out there. And trust me, if you don't understand something, at least 8 other people in this room don't understand it either. So you could be their hero if you speak up.
I have problems with word problems.
Okay, let's do one of those.
Like linear speed, velocity.
Say again?
Is that-
Oh, that kind. Okay, let's do this then. Because I didn't. Good, sir.
Is that on the test?
Hell yeah. Like number 5 on the practice test, right?
Yeah.
So actually, let's do this, because I didn't put all this on the answer key. I said we would finish this in class. Oh, you gotta turn it on, Jeff. It's crazy. Well, everybody's got a practice test, right? I don't have to throw this up here. Go. Number 5. Anybody not have a practice test? I might as well not make assumptions. Flush. You got it? Okay. No, the practice test. Gotcha. Everybody's good. So number 5 is this kind of word problem. I really don't qualify this as a word problem. Focus. Okay. Voice activated. All right. So when you see this kind of problem, does anyone kind of freeze up? So for those of you at home, it's number 5 on the practice test. How many revolutions will a car wheel of diameter 20 inches make in 30 minutes if the car is traveling 60 miles an hour? Even if you don't, if you freeze up, if you don't freeze up, just start writing down, accumulating what I tell you. So what all did I tell you? And give it the right variable names. So can somebody tell me one piece of information I'm giving you? Anything.
Radius is 14.
Radius, I love it. So the radius is 14 inches. Kick ass. Somebody else. What else do I tell you? Give me the right variable.
The speed.
Speed, okay. So the velocity is
60 miles an hour.
60 miles an hour. And of course, the last thing I tell you is the time, right? I give you the time is half an hour. We just write it like that. Is that cool? It's half an hour. 30 minutes, half an hour. Why do I do that? Because I need units to agree within the problem, or else they don't work together, right? Okay. Yeah, it's like if you got paid $20 an hour, and you go, well, an hour is 60 minutes, so 20 times 60 is $1,200. You owe me $1,200. It's like, no, holy shit, no. Right? One is hours, one's minutes. You can't do that. You can try. You're probably not going to like that. Okay, maybe. All right, and I'm asking you, what is it that I'm asking you?
Only revolution.
Can somebody tell me what the variable is related to that? Say again? All right, sort of. So omega is the angular velocity, right? One rotation, one revolution, let me say it like that. What is one revolution? Can somebody tell me what else one revolution, like, what is 12 inches? A foot. Okay, what's one revolution? 2 pi what? Radians. Okay. So all this stuff we can write down from what I told you, from what I remember, and from what I'm asking you, right? Whenever you see revolution or rotation, that is 2 pi radians. Okay, maybe. So how does this all, what the shit? How does this all come together? Anybody have any idea? So can somebody tell me how far we actually travel? What's the distance we go?
30 miles.
Yeah, because we're going 60 miles an hour for half an hour, so the distance traveled, which will give an S, because that's the distance is S, right? I don't know if you guys remember that, S equals R theta. It's the distance we go. We can use the letter D, whatever. So the distance we travel is 30 miles. Is everybody cool with that? That's an immediate thing we can do. Half an hour for 60 miles an hour, we went 30 miles.
And that's R theta.
Say again?
Is S equals R theta?
Yes, S equals R theta. Let's add that to our list of things that we know.
Is that the angular distance?
Theta is the angular distance. I like that. S is the linear distance. And again, you guys, you gotta notice this. What's this symbol mean? Linear speed. How far you go in a straight line. What does this symbol mean? A little chubby W. W. We'll call it W. It means angular speed. How are they related? Isn't linear equal to r times angular? What about this? This is linear distance. This is angular distance. How are they related? Linear equals r times angular. Do you see the relationship between those? So again, if I am on this circle, all right, you're going on a circle, right? Or let's say we're two bugs on a record. Do you guys know records? Do you guys know what records are? Sorry, it's an old man moment, right? Back in the day, we had records. Okay, so we have a record going, right? Some of you guys might even have some. Some people prefer the sound of vinyl. And you're a bug here, and I'm a bug out here, right? So let's say we both go through, we both start here, and we both rotate. Did we go a different angular distance? I don't know if you guys can see that. It kind of drew a little small. The angular distance we went, isn't it the same? Didn't we both go through the same angle? Did we both go the same distance? Which one of us went further? The one closer to the middle or one further out? Which one went further? The one further out went further, right? That's definitely a longer distance, isn't it? Why? Because I'm a larger radius away. The further away I am from the center of rotation, the further I actually go. The angle stays the same. Right? The angle stays the same, but because our radii are different, our distance is different. So that's why, if I'm talking about angles, okay, that's one thing, angles. That's the same for everything. If I've got this line and I rotate it, every point on that line went the same angle. But the further out in the line, that point went a farther distance, yes? Okay, that's why the distance traveled is r times theta. The radius is a multiplier to tell me how far I actually make it if I rotate that much. Okay, maybe. Crazy shit. Okay. So, all right, that was a large tangent I went on. Okay. Now, we're almost there. We almost, believe it or not. Yes?
How did we get 30 miles?
How fast are we going?
60.
60 mile an hour. How long did we go? 60 mile an hour for half an hour. How far do we go? If we go 60 miles an hour for half an hour, don't we go 30 miles? Is that cool? Okay. Those kind of things you have to latch on to. Not every part of a problem is insanely difficult. Not every part of a problem is pre-calc level. This is going so fast for half an hour. We know that. We know it, right? Let parts of a problem be easy. Not every part has to be hard. Okay, so what I'm really trying to get is I'm trying to get this, right? If I knew this, I can convert that to revolutions. Listen. If I went through an angle of 6 pi, how many revolutions did we make? If I go through an angle of 6 pi, how many revolutions do we make? 3. So if I can figure out the angle we go through, and again, so here's the tire, right? If I move forward, doesn't the tire rotate? Of course, right? That's the whole idea. That's how I'm moving forward, right? You're like, good job, Jeff. You figured out the wheel. Yay. Okay. So a point on the wheel is going to go through so many rotations. Yes? So if I can figure out, so do we know how far we made it? 30 miles. 30 miles. Can't I solve for theta if I know the radius? Now what's wrong with this? What's wrong with this? What's the radius? What was our radius? 14 inches, right? So what's wrong with what I'm working with?
It's in miles.
The radius is in inches, the distance is in miles. Okay. So how do I make 30 miles into inches? How many feet in a mile? 5280. And how many inches in a foot? 12 inches. So really want this, so listen. This is the number of inches that we actually travel. So it's the number of inches that a pebble in the tire has gone around. It's the number of inches it's traveled. So what do we got here? We got whatever this is. I don't know. Somebody help me out.
63,360.
Say it one more time.
63,360.
Okay. Is everybody else doing that? Bam, 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 bam. Let's see, does that sound about right? I think it should be bigger than that.
That's how many inches in a mile, so you need to multiply that by 30.
Oh, okay, times 30, right?
I did
You
like
times 30?
5280 times 10. And then times, oh, I didn't do anything after that.
Yeah, times 30, yeah.
Sheet.
I think it's 1,900,800.
Sorry, say it again.
I think it's 1,900,800, but I did that by hand, so I'm gonna.
Neo. Okay, I think that's a little too big.
Oh, yeah, I got it right here.
We're gonna make it, guys. We're gonna make it. Let me get out my nifty freaking blue as all hell calculator. Let's see.
Oh, it's not too big.
30 times 5280 times 12. Bam. Yeah, there we go. Yeah, I think you said it right. Yeah, 1,900,800. Okay, you're right. Inches. Okay. If I go 30 miles, I want that many inches. That's all that says, right? So I really want this to make sense. If I know how many radians I rotate, how do I convert that into rotations? Well, one rotation is 2 pi radians, yes? We all know that. One rotation is 2 pi radians. So 4 rotations would be 8 pi radians, right? Yes? So all I have to do is divide by 2 pi to see how many 2 pi's fit into that, and that'll be 1 rotation each. So right now, this is how far we rotated, this is how far we went, so that's this. R is 14 inches. Can we solve for the angle we went through? Yeah. So see, divided by 14 is that weird thing. So 135,771.4286. That is theta. So to make that into how many revolutions, again, you guys did this earlier. And this is radians, because this is a physical distance. So if it was 6 pi radians, you guys told me earlier, that's 3 rotations, Jeff, because 6 pi divided by 2 pi is frickin' 3. So whatever this is, I divide by 2 pi. Each 2 pi is a rotation, a revolution. So if I divide this by 2 pi, I will get how many revolutions that is. So divided by, you gotta be really careful, divided by parentheses 2 pi. So this tire, if we have a 14-inch radius tire and we go 30 miles, it will revolve 21,608.7 times roughly. See again?
Why do you divide it by 5 then?
So tell me this again. If we went 6 pi radians, how many revolutions did we make? Didn't you divide by 2 pi? Right? Because every 2 pi is 1 revolution. So if I know how many radians, I divide by 2 pi. Or if you want to look at it like this, we can kind of do it like this. 1, 3, 5, 7, 7, 1.4, 2, 8, 6 radians.
That's how many revolutions?
1 revolution is how many radians? 2 pi. So then you divide.
That's how many revolutions it did in 30 miles?
Yes. That's how many times your tire rotated over the course of 30 miles. Right. Now, if you have a larger tire, it would rotate less. Does that make sense? If I had a big-ass tire, it rotates less the further I go. Yeah, it rotates, well, not the further I go, but it rotates a lot less than a smaller tire would. If I had a tiny-ass tire, it's going, yeah, just to kind of keep up. Maybe? No? Okay, there's that one. Let's stick on this kick of word problem kind of stuff. I don't call that a word problem though. It's just collecting what I tell you and putting it in the right place. It's not a word problem. You didn't create your own equation. It's not a word problem. But let's do something that is a word problem. That's interesting. Oh. Does this problem up here look familiar? As soon as that turns off, the Hyperion, right? So an older version of this quiz, I had problem number 5 on there. I decided to be a little nicer on the quiz. Read through number 5 there. Can you see this in your mind? Can you envision this? All right, you're in the plane. Does the problem make sense? Right? If you look straight ahead, don't you have to look down to see a truck on the runway? And then maybe you have to look a little further down to see the other truck because they're kind of like spaced apart. Do you guys understand what's happening? Now come out of the plane, right? Playing a video game, you're going on photo mode. You're coming out of the freaking plane and you're going to look at it. Like there's the plane and there's the trucks. You're going to look at it from here. Can you draw that? Can you draw it? Try to draw it, and then we'll compare what you drew to my picture. Try to draw this situation. Don't forget, angle of depression, if I'm in the plane, and I'm looking straight, angle of depression is measured like this, according to straight out. If I look straight out, it's how much I have to look down. It's the angle I have to look down through. So in the quiz, we all made some mistakes, but we're not going to make those mistakes anymore. Draw this really tiny, it's all right, we'll all survive. Here's one truck, here's the other truck. I'm gonna blow this up in a minute. I don't know, yeah, I didn't give you enough time to draw that, I'm sorry. Can y'all see that? Can y'all see how to get that picture from what I've told you? I mean, if you don't set the picture up correctly, you're never gonna get the problem right. You're gonna have the angles in the wrong place or something. What am I missing still that I haven't put up here that I tell you? Yeah, I'm 1,200 feet. Right, yeah, 1,200 feet up in the air. So let's draw this a little better without the plane and all that kind of business. So I'm 1,200 feet up in the air. I see one truck and another truck. My people have not created wheels yet, so we're a little behind. So if I look down to the further truck, that is 31 degrees. And if I look to the closer truck, that is 33 degrees. And I want to know, what is this? That's what I want to know. This is a classic problem. This is most often considered, well, to me at least, in astronomy. If I know how far away I am from two stars, I can tell how far apart the stars are from each other by looking at the angle they're separated by, right? Maybe. Okay. So what the hell do I do? Can I see any right triangles? I see a few. How many right triangles do you see that would be applicable to my problem? 2 of them. Can somebody help me out? What is this angle right here? I really want you guys to get this. Does anyone remember their geometry? Anybody remember transversals? Parallel lines? Remember those? So don't I have parallel lines? Isn't this a transversal? So that angle is the same as that angle. And then, do I have this the right way around? Sort of, yes. And then this angle is the same as that angle. So that's the trick with that Hyperion tree problem on the quiz. That's how you get the angle up. And again, just to really show you guys, real quick. This triangle right here, this first little triangle, can somebody tell me what this angle is? So this is 33. It's not drawn to scale, correct? So just give me some board license on this. If this is 33, what must this be? 67. Well, 57, yeah. I think you might have said 57. Right? And of course, then, that has to be 33, then, doesn't it? If these two make 90, then these two have to make 90. These have to be the same. Please see that. Nothing major there. So, let me draw each triangle on its own. So I've got this guy. Let me see. I need more room. Maybe I can do some stuff in here. Yeah, all right, let's do this. What do you want to call this? We don't know what this is either. Isn't that one side of one of the right triangles? What do you want to call it? I've already called this X because I'm silly. What do I call this? It's up to you. You can pick. You can call it happy face. You can call it omega. You can call it. What do you want to call it? Say again? No. Just give me a variable. I already used X. Z. Kick hands. Okay, thank you. You can use whatever the shit you want to. Any unknown in a problem, you can give it a variable name. Why do we do that? So we can work with it. We can do shit to it now that I gave it a name. Okay. So, let's draw the triangles. Let's see. One triangle is this first one that's got the Z, right? Does everybody see that? That's the first triangle here. This one. The smaller triangle. The other triangle is the bigger triangle. It goes further out, and it's got a 31-degree angle here. Can somebody tell me how long this is? It's definitely not X. Can somebody tell me how long this is? Say again? Z plus X, right? This is Z, this is X. So this is Z plus X all the way across. So what's really important for you right now is to, this specific problem, I think I've said this before and I say it a lot nowadays, this specific problem doesn't mean anything. This Specific problem, worthless, crap. The type of problem it is, important. Why am I doing what I'm doing? Right? And this, you guys are all like, dude, every day I wonder, right? But why am I doing what I'm doing given this problem? Well, first I draw it, of course I do, because trigonometry is very visual. So I'm going to draw this thing. What's the next thing I do? Well, label it with what I know. So we did that. We labeled it with what we knew. And what's the next thing? Identify what I don't know that I need to know. We did that. We gave them variable names. Can somebody, at this first triangle, do I care what this is? Do I know what this is? Do they ask me what this is? Anything. No, I don't give a shit about that. So don't use sine. Don't use cosine, right? Because that would involve the hypotenuse. I don't care about it. They didn't tell me about it. They didn't ask me about it. Why would I mess with it, right? What trig function relates? Something I know something about and something I want to know something about. Say again? Tangent, cool. So what's the tangent of 33 degrees? Don't tell me the decimal, I don't care. From the picture, what's the tangent? 1200 over z, right? Is that cool? You can see that? I mean, once you get the right triangle drawn, some of you guys still don't quite know which trig, will only use the trig function that relates what you know and what you want to know. I know this, I want to know this, tangent. Don't care about the hypotenuse. So this equals 1200 over z. So then is this cool? Can't I multiply that up and divide that down so I know z is this? So now we know exactly what z is. Go team. Maybe. What do you think I'm going to do next? What have I not put on this second picture, by the way, that I should? What do I know in the second picture that I haven't put down? 1200. So not surprisingly, which trig function am I going to use for the second triangle? Tangent, because I still want these. What's the tangent of 31 degrees? 1200 over z plus x. This kind of thing happens often in a lot of different word problems. You get two variables, and one of the variables you don't care about. Which variable do I not care about? Which variable do I definitely want? Because it's the question. X is the question, right? Z, I didn't want it. Why did I have to call it? Because it's part of the problem. I got to use it. I got to use Z. Shit. But I don't care about it. I want to know what X is. So, let's do the same thing we did here. Let's multiply this up and let's divide this down. So isn't X equal to 1200 over tangent 31 minus Z? Is that cool? You guys see that? Subtract Z. Now I know X. Can you plug this in there and then throw the whole thing in your calculator? Yes. So what is the point of these kind of problems? Draw the problem. Label the drawing. Look for right triangles. Set up your trig relationships, right? That's exactly what we did. Draw the problem. Label the drawing. Identify your right triangles. Pick your trig. Because now, X equals 1200 divided by tangent 31 minus 1200 divided by tangent 33. So let's all take a minute. Try to figure out what that is. Put it in your old calculators. If you don't have an old calculator, then hang out. Let me make sure I'm in degrees, yes. 31. Don't forget to close that parenthesis on your tangent. Oh, let me show you what I'm doing. What do you guys get?
149.
Yeah, almost 150 feet, so 149.3 feet. So they're about, those two trucks are roughly 149.3 feet apart. That's how far apart they are. Crazy sauce. Now again, I mean, trig, new, relatively new to us, not brand new. We've been working with it for a while. You need to be able to, if you can find a right triangle, you need to be able to do any trig shit to it you need to. That's what trig is based on, is right triangles. So of course, in a word problem, which trig function you use is dependent on which sides do you care about. I would never use cosine or sine because I don't care about that. I'm not given information about it, and I'm not asked about it. So why would I use sine or cosine that needs the hypotenuse? I would never do that. That doesn't make any sense. Okay, maybe. Okay. Let's see. Let's try. Well, let's do this. I'll tell you what, let's do this. I didn't put the graphing problems on the answer key, just because I wanted to do them together. So what I'm talking about is like these last two. Oops. These last two. So I kind of want to do them together. So let's do that real quick. Let's do 7 and 8, and then I'll just open it up to, we could do another word problem, we could do whatever you want. Before I do that, before we do this, let me just ask real quick. Just to remind you guys, there will be a part 1 of this test, and when you're done with part 1, you'll bring it up, and then you'll get part 2, and then you'll be allowed to use a calculator on part 2. Part 1 will be, what's the cosine of 45 degrees? What is the sine of 7 pi over 3 radians, right? So you won't be able to use a calculator. You have to tell me what the exact answer is. You have to draw your reference angle. You guys with me? That will be part 1, no calculator. And then you can use a calculator in part 2 to do all this funky shit like that, right? Okay, maybe. So if I ask you right now, what is the cosine of 45 degrees? Don't tell me. Do you know what it is? Okay, tell me. Rad 2 over 2. I like it. And what's the, and again, I really hope you guys understand. I'm trying to help you come up with a way to remember it, right? I try to show you, I don't have them memorized. I don't have them memorized. I don't. Because I only have so much space up here, right? If I remember anything else, if I memorize anything else, I'm going to forget something. I have to make room. So what I do is, I've explained this before, if I'm trying to figure out cosine or sine, is how far away they are from where they like it. Cosine likes it on the x-axis, sine likes it on the y-axis. Right, so at 45 degrees, aren't they both equally distant away from where they like it? So they both should agree. So it's either 1/2 rad 2 over 2, rad 3 over 2. So it must be the rad 2 over 2. It must be the one right in the middle. So when I say something like, what's cosine of 60 degrees? Cosine likes x. 60 is way far away from the x. It's closer to the y. So cosine should be smaller. So what's cosine of 60? 1/2. It should be the smaller option. Does that? And again, if you don't like my way of doing it, that's completely fine. I am my own person. You are your own person. If you want to just straight up memorize everything, feel free. You're younger. You have more space in your brain. I love it. Do it. Fill it up. I would highly recommend you don't do that, right? You need more space for the future, right? Okay. So let's look at number 7. Okay. So on the actual test, I'm gonna make like part A will be amplitude, part B will be phase shift. You know, I'm gonna kind of break it down for you. You are gonna have to remember how to find each thing. So we're talking about cosine here. What does a cosine just look like? The basic cosine, what does it look like? What's cosine of 0? Cosine likes x. What's cosine of 0? 1. It's happy here. 0 degrees is on the x-axis. So it starts at 1. So it's different from sine. Sine, of course, starts here and goes. Cosine starts at the top and goes from there. It's got the same stuff here. So it's 0 here, -1 here, 0 here, 1 there. So that's the basic cosine. Okay. And of course it keeps going, whee, yeah. Repeats that forever, right? So if I go a little further, I always think of cosine as some kind of a weird octopus thing, or it looks like a horned beast or something. I don't know. Okay. That's the basic cosine. It's got the same anchor points. You just gotta remember what it does at each. So, we've got this thing. Amplitude, easy. What's the amplitude? 3. So 3 cosine. So the amplitude is 3. What does that mean again? It's gonna go up to and down to -3. People always get that confused. It's actually 6 from top to bottom. 3 just tells me how far it gets away from the middle. Sort of like a radius. Here's the center. It's 3 away there and 3 away there. Right? So that's what that means. Amplitude is how far from the middle I get. Phase shift. How do I figure out the phase shift? What do I have to do? Say again? Factor the inside. So if I factor the inside, what comes out? Yeah, 4 comes out. So what's left here? Yeah, because when I take something out, I divide it out. 4x divided by 4 is x. Pi divided by 4 is pi divided by 4. Yes?
Do we have to factor it, or it doesn't matter if it's not factorable?
Oh, it has to be factorable. Period. Period. It just is. Now, we're not going to see a problem like cosine of 4x squared plus pi or something. We're not going to do that here. That's for later classes. Does it make sense? So it will always be factorable. Does that make sense? Because it's always going to be either that's 1 and I'm done, or that's not 1 and I divide by it. So it's always factorable, what we're going to look at. I like it. So what does this do? Shifts it where? How much? Left? 5 or 4. All right, I like it. And then I ask for the period. So what number affects the period here? Yeah, the 4, right? So 4 is what we call k. So to get the period, it's 2 pi divided by k. So the period is now pi over 2. The period, it normally takes it 2 pi to get through stuff. Now I've squished it so much, it's going to make it through this whole thing in pi over 2. It's been squished. Okay, maybe. Let me see, what else do I ask for? Blah, 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 blah. Sketch the graph, but I didn't. Let me do step size. Step size. Does anybody remember how to do step size? I don't ask for it, but it's a good thing to know. So normally it takes it 2 pi, and I cut that up into 4 parts, right? So it's 2 pi divided by 4 is pi over 2. And normally the step size is pi over 2. Now, the whole period is pi over 2, and if I cut that in fourths, I I get pi over 8. That's the step size. And I don't ask for this here because you actually don't need it, but it's still a good thing to do. Begin, end. So cosine starts when this is 0, and cosine ends when this is 2 pi. Cosine of 0 is where it starts, cosine of 2 pi is where it ends. So if I solve this, don't I get negative pi over 4? Why does that make sense? It used to start at 0. How much did we phase shift? Pi over 4 back, right? So of course I'm starting at negative pi over 4. That's kind of nice. It's kind of nice to see this agree with this. And where do I end? Well, if I subtract pi, divide by 4, I'm going to end at pi over 4. Why does that make sense? Well, how far apart are those? Negative pi over 4 up to pi over 4. How far apart are those? Pi over 2. It's pi over 4 minus negative pi over 4 is 2 pi over 4 is pi over 2. Why does that make sense? Because the period is pi over 2. It should take it pi over 2 to get through its whole cycle. Okay. And again, do you see how this is really unnecessary? I keep saying that, but it's really nice to kind of confirm what you did. Okay. So now we know what the basic cosine looks like. Let me take some of this away. All I care about is this middle part for the moment. Then we can just draw arrows on the outside. So now ours is going to start at negative pi over 4. It's going to end at pi over 4. The step size is pi over 8. Yes? So again, what's normal sine do? It's 0, pi over 2, pi, 3 pi over 2, 2 pi. So I'm kind of just doing that. I'm trying to figure out where's the next major thing. Where is it 1? Where is it 0? Where is it negative 1? So it's going to happen. What is negative pi over 4 plus pi over 8? Well, if I make this negative 2 pi over 8, if I add pi over 8, where do I get to? Pi over 8, negative pi over 8. If I add another pi over 8, I get to 0. If I add another pi over 8, I get to pi over 8. And if I add another pi over 8, 2 pi over 8, pi over 4. Sweet. It all fits in there. So what does cosine do? Again, what's the amplitude? 3. And cosine starts where? Wherever it begins, it starts at 3 in this case, 11. Starts at the maximum. So it's going to be 3. And then what's it? And then it goes to 0, negative 3, 0, 3. So there it is. So I smooshed it and I moved it back a bit. I smooshed this and I moved it back a bit. Bam. And of course I stressed it too, but it's all good. Okay, maybe. Now when you do these problems, you do not have to graph the base graph. You don't have to graph this. Because the way that we shift these is less direct. We used to graph like a parabola and then we'd actually move each point. We don't really do that here. We kind of do it through this stuff. So you don't have to graph the base graph, but it's good to know what the base graph looks like. Okay, maybe. So that's 7. What if I would have said secant? What if this problem would have said 3 secant 4x plus pi? How would that be? How would this change? Would any of this work change if it said secant? Nope, none of the work would change. Just this wouldn't be the answer. I'd have to put my little cups up here, right? Where would my vertical asymptotes go? Because again, Why am I talking like this? Secant is how related to cosine? Secant x is 1, not inverse, be careful. 1 over cosine x, reciprocal. Inverse has a different meaning. It's like the opposite function. So if it was secant, it would be like this. There would be a vertical asymptote wherever it's 0, right? This would be the secant, would be these cups. Here, there, here. So if I ask you cosecant or secant, you pretend like it's sine, cosine. You do all the work like normal, and then you put the little cups, and that's your answer. Because they are related. Secant is directly related to cosine. That's why it makes sense. I should graph cosine, and then on top of that, I can graph the secant. Maybe. Okay, now, what does tangent look like? Oh shit. All right, I'll leave all this up. No. Uh-oh. We've seen some stuff here before. Do you guys know what the basic tangent function looks like? Somebody describe it to me. It looks a lot like something else we've looked at before. Say again? Cubic. Kick ass. So the basic tangent function looks like this. Where are these at? What's on the bottom of tangent? Cosine. Vertical asymptotes are where cosine is 0 then, correct? If the bottom is 0, gotta throw that shit out. Gotta put a wall there. That's weird. Don't go there. When is cosine 0? Say again? Yes, and when's y1? What angle? Pi over 2 and negative pi over 2, right? So there's an asymptote at negative pi over 2 and a pi over 2. So that's what the tangent, and of course it continues forever in both directions, right? Just forever and ever. Why? Because it can go around the circle. Okay. So what is its normal period? Sorry? Pi. Right? That's how far apart negative pi over 2 and pi over 2. It takes pi for it to get through its whole image, and then it just repeats that image forever in both directions. Okay, maybe. So, look here how I say this. Use the quote amplitude appropriately. There is no amplitude for tangent, is there? But can somebody tell me what points I can use here and here? When is it 1? When is tangent 1? What angle is tangent 1? Well, tangent is sine over cosine. So when does sine equal cosine? 45 degrees? Pi over 4, right? That's right in the middle of x and y. So that's where they're going to be equally happy and sad, right? They're both equidistant from where they like it. So tangent is 1 where sine and cosine are equal because tangent is sine divided by cosine. So that's 45 degrees. So at pi over 4 and negative pi over 4, it's 1 and negative 1. Okay. So when I say use the amplitude correctly, at those positions should be where it hits. In this case, what's the quotes amplitude? 3. What's the negative going to do to this? Flip it. So it's going to end up looking like this. Okay. Okay. All right. Maybe. So let's figure it out. So the amplitude is 3. It's been reflected around the x-axis. What is the period? Well, what's the original period? Let me write the function down. What's the original period?
Pi.
Pi. And what's k?
So pi.
Also pi. So now the period is 1. Same stuff, right? It works the same way, the cosine, sine, tangent, it works the same way, you just gotta use the actual period. For tangent and cotangent, the period is normally pi. Now it's been smushed by pi, so now it's 1.
So it's not 2 pi?
So again,
It's not 2 pi?
because again, cosine and sine takes 2 pi to get through its whole thing. Tangent only takes pi. So its normal period is, so tangent, cotangent, period's pi, because that's how long it takes for it to get through its stuff. And then it just repeats that. Sine, cosine, secant, cosecant, they're all pi over 2. I'm sorry. They're all 2 pi because it takes 2 pi for it to get through its whole cycle. Or for you guys, it would look like. Okay. Maybe. This is all new, I know, for a lot of you guys. For some of you guys, this is old, which is great. Just enjoy it. Okay. What do I still have to do here to help me figure out the phase shift? What do I have to do here? Ooh, you're good. If I take a pi out, what's left? 1/4, good. All right, take a pi out, 1/4. So what's the phase shift? How much to what direction? 1/4 to the right. Okay, I like it. So again, on the test, each of these will be like A, B, C. I'll kind of step you through the work. I'm not going to tell you how to do each thing, but I'm going to step it. You don't have to remember all these steps. You have to remember how to do it. Okay, what about begin, end? The normal tangent begins at negative pi over 2 and ends at pi over 2. So it's going to begin when the inside is negative pi over 2. It's going to end when the inside is positive pi over 2. So the first vertical asymptote is a negative pi over 2. The last one is at pi over 2. So then I can just solve this. Do you have to do this step? No, you don't. So let's see if we get familiar looking stuff. If I add pi over 4 to negative pi over 2, I get negative pi over 4. If I divide by pi, I get x is negative 1/4, which matches with, what happened? Oh, that's right. This is weird. You won't see this directly because it doesn't start at 0, it starts at negative pi over 2. It'll be okay. So we're going to start at negative 1/4. And here, if I add pi over 4, that's 2 pi over 4 plus pi over 4 is 3 pi over 4. And if I divide by pi, I get 3/4. Okay. This one, the phase shift, it doesn't start at 0. So therefore, the phase shift, you can't really see it directly because it doesn't start at 0. But how far apart are these? How far apart are these? Negative 1/4 up to 3/4.
4, 5, 3, 4,
4
4.
4, which is 1. They're 1 apart, and what was the period supposed to be? 1. Okay, good. It's matching. Okay, so what does this thing look like? Alright, so I've got, there we go. So now it starts at 1/4, negative 1/4. The step size, let's see if you guys are cool with this. So the step size, once again, I don't know if you guys, so there's a point where the vertical asymptote is. then there's the point where it goes to -1, then there's a 0, then there's 1, then there's so I broke it up into 4 parts again. It's pretty much always breaking it up into 4 parts. So the period is 1, break that up into 4 parts, I step by 1/4. That's kind of beautiful. Let's see if this matches up. So a -1/4, then it's 0, then it's 1/4, then it's 2/4, then it's 3/4. That matches up with where I'm supposed to end. Kick ass. What goes at the ends? I pretty much just gave it away, but what goes at the beginning and the end? What goes there? Asymptotes. So now it's at -1/4 and it's at 3/4. So the middle is 1/4. That's where it goes through 0. Remember, it's reflected, right? It's reflected. So what am I going to do here? Normally, at this point, I go to -1. Now it's reflected, but it's also multiplied by 3. So now I'm going to go, normally it'd be negative, but now it's positive. So I go to 3. Right? Then here, then normally here I would go to 1, but now it's reflected and it's multiplied by 3, so I'm going to go to -3. So now it looks like this. No, Jeff. Okay. It's difficult to get the curve in there. It's not very curvy. Okay. Crazy. And how do you verify this? Well, you can just plug it in the calculator and graph it. That's fine. Do that at the end, right? If your work does not match with your graph, that's when you lose the most points, just like before. So resist the urge to copy from your calculator. So those are the ones, I did not put them on the answer key, I just wanted to do them together in class. Let me go ahead and give you that answer key, why not? It's a very short little answer key because we did a few of these in class. Sure. Sure. By the way, on number 4, I forgot about this, but on number 4, you see where it says this here? Find the value of theta. We can't do that yet. That's from section 8.3. So next, section 8.3, real quick, I'm not going to throw a ton at you. If I knew sine of theta was 0.7, and I want to know what the angle is. Well, for example, if I knew the square root of theta was 0.7, how would I figure out what theta is? If I knew the square root of theta is 0.7, how would I figure out what the theta is? Come on, you guys know. Square it. Of course, right? Undo the freaking thing. Do the opposite function. So in section 8.3, we're going to learn about the opposite function. In fact, if you look on your calculators, can you see the inverse sign that sits above the sign? If you look on your calculator, you'll see, if you find your sign, where's it there? Right above it is inverse sign. So that's section 8.3, right? So I just forgot, I didn't notice I had a problem from 8.3 on there. Just don't worry about this part if you're like, how the hell would I do that? You can't do it yet. Yes?
For number 2, the negative care if we answer in positive or negative, because I converted the degrees to positive.
Oh, I see. As long as you make it a real, like, did you make negative 54 into 306? Or what'd you do?
The, particularly C, I just wrote 2 10 degrees, which I think lines up.
Yeah, that's fine. As long as it means the same thing. So if I go back 150, that's the same thing as going forward 210. So I love it. Nothing wrong with that. They both end up in the same place. So any specific position has an infinite number of angles that gets me there. Because I can turn, I can go backwards, it's crazy, yeah. So that's fine. So let me know if anything looks weird, if it disagrees with what you did.
Can you go over product number 6 and product 6?
Yeah, okay. So several things that you need to know going into that kind of problem. First thing you need to know, for example, can somebody tell me what the cosine of 30 degrees is? So cosine likes which axis? The x-axis. 30 is close to it. It should be the bigger option, square root of 3 over 2. That's how I remember it. Don't have it memorized. I have to think like that for just like 3 seconds. So this is the square root of 3 over 2. Right? That's the basic fact you need. It's one of them, one of the basic facts you need to know. You got to know all the angles in the first quadrant for at least sine and cosine. Why do I only need to know sine and cosine? Because tangent is sine over cosine. Right? So real quick. What's the sine of 30 degrees? Now that is 1/2, because it's far away from where it likes it. It's close to the x. It doesn't like it there. It's going to be smaller. 1/2. So can somebody tell me what cotangent of 30 degrees is? Well, what's cotangent? What's cotangent of theta? Whatever what? Cosine theta over sine theta. It's the reverse of tangent, right? It's the reciprocal. So this is cosine of 30 over sine of 30. What's cosine of 30? Rad 3 over 2. What's sine of 30? 1/2. The 2's cancel. Rad 3. Bam! So you definitely don't have to memorize tangent and cotangent for damn sure. And you sure as all hell don't have to memorize cosecant and secant. Because if you know sine, you can figure out cosecant. You just flip it. Maybe. Okay. So, what if I ask you, what is the secant of 330 degrees? Okay. Let's piece this together. I'm going to ask you to show me reference angle work. So what quadrant am I in? I didn't quite make it to where? 330 is not quite all the way around, right? So how far away from that did I stop? 30 degrees away, right? That's the reference angle. How far from the x-axis do I end up? 30 degrees. So this is equal to, is secant going to be positive or negative there? Well, let's do this. Isn't this equal to 1 over cosine? Right? That's what secant is. And what's cosine here? Is it positive or negative? Cosine. Positive. So this is the same thing as 1 over positive cosine 30. That's the same triangle as a 30-degree angle up here. Those are the same triangle. So cosine of 330 is the same thing as cosine of 30. They are the same thing because they make the same triangle. Do you guys see that? So if I drew a 30-degree triangle in the first quadrant, do you see how those are the same triangle? So they have the same x length. What is cosine of 30? What is 1 over rad 3 over 2? Right? 1 divided by something is a reciprocal of that thing, yes? So it's just 2 over rad 3. And what do I have to do to this? rad 3 over 3. You're a weird looking 3. Poor little dude. That's what I want to see on that kind of problem, right? And that's what you have to know on that kind of problem. So I ask you about secants, okay? You don't freak out, because it's just immediately 1 over cosine. You can immediately do that. Then you get the reference angle, and you figure out, is cosine positive or negative? Well, it's positive, because x is positive here. Maybe. Again, if you want to memorize that secant of 30 equals 2 rad 3 over 3, that's your thing. I wouldn't want to do it, but you can do it if you want to do it. I highly recommend you don't. That's really silly. It's wasting brain space. Do you guys understand that just memorizing the first quadrant, because everything is based off of reference angles. So if I just know the first quadrant values, I'm golden. And all I got to do is know sine and cosine, because I can build tangent, I can build cotangent, I can flip it for secant and cosecant. That's all I got to do is memorize sine and cosine. Okay. One little thing that's going to become big pretty quickly, I want you to notice something. Let's do it this way, and then we'll do it a different way. Yeah, let's do this 2 different ways. All right, so help me out, guys. Help me out. What is y squared plus x squared?
H squared.
H squared. Right? All right, that's, you're like, yeah, Jeff, good job, yay, Jeff. Let me put a little angle here just because. Stay with me real quick. I'm just going to do this a little quickly. If I divide by h squared, why would I do that? I don't know, I'm just playing around with shit. Don't I get this? Right? Can somebody remember what is x divided by h? What is that defined to be? Cosine. So this is cosine. And what's y divided by h? Sine. So then we get this fact. Sine squared plus cosine squared equals 1. Sine squared theta plus cosine squared theta. By the way, real quick, if you write this, what's wrong with that? That's not correct. What's wrong with that? You're like, I don't even know the problem. No, you don't have to know the problem to know that's not correct. What is wrong with that?
There's no base.
There's no
Base or like degree.
input. That's sort of like telling me, well, the answer, Jeff, is square root equals 11. What? Square root of what is 11? So you have to have cosine of b, or cosine of theta, or cosine of whatever the angle is. Same way square root with nothing inside doesn't mean shit. Putting cosine with nothing inside of it doesn't mean shit. Do you guys see that? It's weird because we're not that used to, we got log, but we're still not that used to log. We're not used to functions with letters that look like little words, but they still need an input, just like square root needs an input to make sense. Cosine needs an input to make sense. Okay, that's a little side note, sorry. Another way to see this, do you guys still have, yeah. If anybody needs this, let me know. This little guy, whoa, this giant guy. You need it?
Yeah.
I use it.
All right, so notice this. I want you to realize something. I don't like teaching it based on this picture, but I do like you to notice some things about this picture. It's a little busy up here. Let's see. Get out of here. Get out of here. Unit circle. There are points sitting on the unit circle. That's the reality. cosine tells me the x piece, sine tells me the y piece. But if I am sitting on a unit circle, the equation of this circle is x squared plus y squared equals 1. Let's check this. If I take this point right there, what is the square root of 3 over 2 squared plus 1 over 2 squared? What's the square root of 3 squared? Square root of 3 squared. 3. And what's 2 squared? Holy shit. So I get 3/4 plus 1/4, and that is 1 check. Every single point on the unit circle, and each point relates to sine theta and cosine theta, right? Cosine theta is the x piece, sine theta is the y piece. Since they sit on the unit circle, they have to match the equation of the unit circle, which says the x squared plus the y squared is 1. So the cosine squared theta plus sine squared theta has to be 1. That's another way to find this relationship. Okay, maybe. Anyway, so after we finish up chapter 8, the very next thing we're going to do is to start looking at trigonometric identities, which is normally everybody's absolute favorite, right? Just to give you something to look forward to. I'm hoping to make it simpler. We shall see when we get there. Was that really difficult to understand? So remember, cosine likes x, sine likes y. And why is that the definition of the circle? Because isn't there a triangle here? Shouldn't the x piece, yeah, they're square, and the y piece and the 1 meet Pythagorean theorem? And where should it do that? Everywhere, because everywhere I can draw a triangle. So that's why that is the definition. That's why that is the equation of that circle. Okay, that's a little preview of stuff to come. But Samaya, that's kind of related to your question from before. So that would have worked, yeah, the approach you're trying to take, but you didn't need to do that, yeah. So I still get people, real quick, if I only told you these two things, if I told you sine of theta is 1/3, and theta is in the second quadrant. So this is like the problem in the quiz. And I say, find the other trig function values of theta. How the hell do you do that? Well, what are trig functions based on? Right triangles. So I can immediately draw a right triangle. And I know which side is 1 and which side is 3, because it's sine, right? So which side is 1? The y side. And which side is 3? Hypotenuse, right? So if I tell you this, you can immediately draw a triangle, because you know the ratio of the sides. That's what trig functions tell you, is the ratio of sides. Okay, oh, so I know that's 1, that's 3. So then to figure out like cosine, what do I have to know? Gotta know this here, right? And how do I get this? Yeah, so it'll be square root of 3 squared minus 1 squared, square root of 8, which is 2 square root of 2. And then I can make everything. Once I get that last side, I'm golden. I can make every trig function. It's just the ratios, right? You guys with me? Okay. The fact that it's in the second quadrant, what does that mean? What's going to be negative? X, so cosine's going to be negative. Sine is positive, right? Sine is positive. Cosine is going to be negative. What else is going to be negative? Tangent and cotangent, because there's sine divided by cosine, right? What about secant? Secant's automatically negative because it's 1 over cosine. What about cosecant? Positive because it's the flip of the sine, right? So that's what you can draw a triangle immediately when I give you a trig function equals a fraction. You can draw the triangle immediately. And then you can make all the ratios, and then you can just be careful, okay, which things are negative, which things are positive, right? You could even be really nice and crazy and just tell yourself, well, this is negative, this is 1, that is 3, and this is negative 2 rad 2 because it's back. And then you can make all your trig functions on that, and everything comes out negative that's supposed to be negative then. So you can do it either way. You can put the negative on at the beginning, or you can put the negative on at the end. Okay, maybe. Okay. Oh. Yeah, you got all that back last time, I think, right? Yes. Oh. Christian. Oh, all that stuff. I was pointing that way. Just everything we were just talking about. All right. Anything lingering? Anything else? Very yes.
Number 4, practice this.
Number 4. Oh, that's just like this one we were talking about, right?
You see like 3 pi over 2.
Say again.
I
Sorry.
think the part it says like and 3 pi over 2.
Oh. Help me out. Help me out. This is 0 degrees, right? 0 radians. What's this? Pi over 2. What's this? Pi. What's this? And what's this? 2 pi. So which quadrant has angles between 3 pi over 2 and 2 pi? 4. So I know in the 4th quadrant. So it's another way of me saying you're in the 4th quadrant. So then you know the x stuff is positive and the y stuff's negative, right? I like it.
I have a question.
Yes.
On 7.2, like 6 through 9, can we like do 6 maybe, because I don't understand how to do this.
So 6. Oh, okay. So there's something we can notice. So when I'm at 30 degrees, for example, sine is 1/2. Is that cool? And cosine is rad 3 over 2. Okay, I can't write words. Anything? There. At 60, don't those just turn around? So the idea is sine of some angle is equal to cosine of pi over 2 minus that angle. They're offset by 90 degrees. So cosine of 34 would equal sine of, and this is what they mean by complementary, right? Complementary angles. Complementary means makes 90. So cosine of 34 equals 90 minus 34. What's 90 minus 34? What's 90 minus
63?
56. Right? So cosine of 34 will equal sine of 56 degrees. And again, what's the other way to look at this? Because sine and cosine both grow in opposite directions. Sine gets to 1/2 at 30, cosine gets to 1/2 at 60. They're always offset by 90. We know they're offset by 90 just looking at their graphs. Okay. So like cosine of pi over 3, well, you can think of it in terms of degrees if you need to, right? Pi over 3 is how many degrees? Pi over 3 is how many degrees? Yeah, pi is 180 degrees, divided by 3 is 60. That's cosine is 60, would equal sine of 30. I like it. I like it. Okay. Maybe. Okay. So that's something kind of good to notice now, is how those kind of work. And, another way to look at that is, if I have a triangle, let's say this is 30 and this is 60. Cosine of 60 would be x over the hypotenuse, correct? Yes, just by basic definition. What would sine of 30 degrees be? Well, sine of 30 degrees, I'd have to look at it like this. Sine of 30 would be x over h also. It's another way to see why they're offset by 90. Because what do these two angles have to add up to be? 90. And if I talk about cosine of this versus sine of that, I'm turning my head, I'm using the same sides. But I'm using the angle that is off by 90 from the other angle. That's why that identity makes sense. Okay. Maybe. So, for example, real quick, if I have a triangle, let's just say A, B, C, and this is, let's say this is 50 degrees. So what's this? 40 degrees. So what is sine of 50 degrees from the picture? No, I mean from the picture, what's sine of 50? Defined to be. Which sides? A to C. It's the y side of the hypotenuse, A to C. What's cosine of 40 degrees? So I can turn my head like this. It's going to be x side over the hypotenuse. It'll also be A over C. No matter what these angles are, right? This could have been, if this was 57, this would be 40, what do you got, 33, John, good job. The same thing would happen. That's why, and so graphically we know they're offset by 90 degrees. Triangularly, sure, just to create a new word, we know they're offset by 90 degrees. Okay, maybe. So if I know that cosine of 20 is A, what is sine of 70? Also A. Yeah. That's the idea. They're offset by 90 degrees. Okay. Maybe. And again, just to remind you about the graph, here is sine, right? Here is cosine. Here they're offset by 90 degrees. This, if I put it back 90 degrees, it becomes cosine. If I push it back 90 degrees, it becomes cosine. They're offset by 90 degrees. That's why this complementary angle idea works. here it is. Cofunctional identities. Everything's offset by 90 degrees from everybody else. Oh, that'd probably be best. Wait, you can see that? Yeah, you can. Okay. Right there. Okay. Anything else? Practice test from the quiz. Don't forget your quiz corrections are due tomorrow, right? So work on those if you want to right now. So what do you do if you're really behind on homework right now? The test is tomorrow, right? And let's say you haven't done any of chapter 8 homework. Maybe you haven't even done like 7.3, 7.4 homework. What do? Do you just go, oh, I'm just gonna, oh. What do?
Every other problem.
Yeah, or even less than that. I mean, you need to try some problems from the sections, right? Eventually, you can try to finish the homework. Right now, you want to get practice for the test tomorrow. Right? I don't know if you guys really understand what I mean by that. So yeah, turn in what you did. Great. I'm going to go, what the hell, finish this. Or I'm hopefully not going to say what the hell, but, right? And you're going to go, okay, I did what I could. I will finish it if I can, right? You make it your own. Don't leave entire sections unlooked at. That is the way to make certain you will not do those well at all in the test. Okay, maybe. Can you guys do me a favor real quick? Can you, so for example, if I want to make a triangle with like 10 degrees in the base, I might do it like this. Try to make this really tiny. Do you see what I mean? Can you make a triangle that has 60 degrees? Can you draw a triangle that has 60 degrees right there? So it's going to be bigger than 45 degrees. Can you eyeball that? Make a triangle that's got 60 degrees here instead of 10. This would be about halfway. So 60 would have to be more than that. In fact, it has to be a decent amount more than that. So let's do it this way. Might be easier this way. So this is about 45. So 60 should be maybe right there. There we go. Right. So which side is bigger, X or Y? Y is definitely bigger, right? And which side, which trig function tells me something about the Y side? Sine. So again, that's why. That is a physical, in-your-face reason why sine of 60 is bigger and cosine of 60 is smaller. Right? If I made a 30-degree angle, so see, this is 45, so 30 would be like there. Now which side is bigger, X or Y? X is much bigger than Y. So again, that's why cosine gets big the closer the angle is to being flat, the closer the angle is to being on the x-axis. Because then the x piece gets way bigger than the y piece does. And vice versa. The closer this gets to 90, the bigger the y side gets. Okay. That is why they act the way they do. Yes.
Did you send me a copy of that?
On the practice test? This one? I thought we did this one.
I said, can you send me a copy?
Oh, a similar problem. Alright, let me see. Alright, here we go. Alright, here we go. Number 60. Okay, I like this. So a wheel of radius 8 inches. Okay, let's keep track of what's going on here. So I got radius 8 inches. 15 degrees per second. What is that? What variable describes that? Omega. Good old chubby, right? Chubby W. I like that chubby W. He's chubby, so it's got like wah, wah. 15 degrees per second, which makes sense because it's theta over time. That's what that is, right? They ask me for the linear speed. What's the formula for V in terms of other stuff, in terms of angular stuff? Do you guys remember? It's R W, yeah, R omega. And don't I know, didn't they give those to me? There's one problem with something they gave me. There is one choice they made that was really bad that we can correct. Say again?
15 degrees.
Yes. Why is 15 degrees a bad choice? Sorry? Well, no. You mean here? That's rotations per minute. Okay, so again, when I'm dealing with angles, which units are better, especially when the angle is out on its own? Radians are so much better because they're an actual physical measurement, right? So we first have to change 15 degrees. How do I change 15 degrees to radians? So I want to kill degrees and change it to radians. How many radians is how many degrees? Good. What is that? 12? Is that pi over 12? Yeah. And then I got everything, don't I? So what's the omega now? Omega is pi over 12 radians per second. So I can figure out the linear speed. Oh, actually, holy shit. Well, that's kind of silly. Look at the last question. I always hated problems like this where the last thing they ask is the first thing I get. I'm like, did I do something wrong? So we already have the last part of the question, right? Angular speed in radians per second. Done. Linear speed. Isn't it R times omega? Sweet. Right? Okay. So it really is every problem like this. Give a variable name to what they tell me, and then write the equation of what they ask me. And then I'm trying to see, okay, how do I have everything I need to plug in, right? And if I don't, how do I get what I need? Did I not use something they told me? And one thing to really pay close attention to, if I say rotations or revolutions, that's huge. That's something that people normally skip over. If I did 3 rotations every 20 minutes, that is 6 pi radians every 20 minutes. That's huge. That's a lot of information. So look for rotation and revolution. Look for that. That's huge. So the only thing we have left to figure out, because here I just got to plug stuff in. 8 times pi over 12, blah, blah, blah. Okay. And this will be inches per second. But then they want to know the angular speed in rotations per minute. So how the hell do I do that? Well, I know the angular speed in radians per second. Say again? Multiply by what?
I know, what was it, like 60 seconds?
60 seconds is in 1 minute, 11. So now I got radians per minute. How many radians are there in one revolution? One rotation? 2 pi radians. There we go. So you do pi times 60 divided by 12 divided by 2 pi. Yeah. So look, the pi's cancel. 12 goes into 65 times. So you get 5 divided by 2 is, I get 2.5 rotations per minute. Crazy. RPMs. You all see that gauge in your cars. But that's what it means. It means rotations per minute. So again, any problem I give you like that, it's all about collecting what I tell you and writing down what I ask you. So collect what I tell you, write down the equation for what I asked you, right? Okay, maybe. All right. We're almost to time. Any other questions? Don't forget I'm in the Math Study Center today. I'm in the Math Study Center, well, I'll be in the classroom early tomorrow, as always. I'm in here starting at 7:15. So you can certainly come and ask any last minute questions. And if you're gonna make corrections, come into the Math Study Center, get some help from me or from some tutors, get some help. Get as many points back as you can. What else is due tomorrow besides homework through section 8.2, right? Homework through section 8.2. We didn't do section 8.3. What else is due tomorrow? Quiz corrections. What else? The last test corrections, right? Okay. If you don't turn those in tomorrow, does that mean you can never turn them in and never get any points? Yeah. No. If you wanted to be, Sue. But no, you can turn those in later, but the later it is, the less points you get back. It's that simple. Okay. All right.